Yeah, hello everyone. I am Dr. Neelakanteswar Rao. I'll be discussing a series of lectures on Power Systems 1 course. In the last lecture, we have seen calculation of inductance due to internal flux. In today, I'll be discussing about how to calculate inductance between 2 points external to a conductor. So that is what we'll be seeing today. So let us go to the topic now. So why we consider an isolated conductor is we want to neglect the effect of the flux due to any other conductor in vicinity of the conductor of interest. So that is the reason why we consider the conductor of interest to be isolated from rest of the conductors. And also we consider a solid single strand conductor which is of round shape. So let us consider a conductor . So let this be the conductor. Let some current flow through it. So let us show that current flow with this red mark. Here I am using a red mark to show the flow of current in the conductor. So now we'll be considering 2 points external to the conductor, and we'll see how the flux linkages behavior will be there between those 2 points. And we know that whenever a current flows in a conductor, flux surrounds it according to Ampere's law, and the path of this flux will be circular, and all these circular flux lines will be concentric to this conductor. That is, they have same center. So let us consider 2 flux lines which are concentric in nature and they are external to the conductor. So let this be one flux line. Let this be another flux line. So both these flux lines are concentric in nature. Now let us assume that the current, let the current flowing through the conductor be capital I amperes. Here capital I represents the phasor current since we are dealing with AC line. Now let us consider 2 points external to the conductor. So let one point be at a distance d1 and let this point be some p1. Let another point be at a distance d2 and let this point be p2. So I have basically considered 2 points p1 and p2 at distance d1 and d2 from the center of the conductor. Okay. Now for analysis sake, what I do is, as we have done for the calculation of flux linkages internal in the conductor, that is due to the flux which is internal to the conductor, there we have considered a tubular element for analysis. Similarly, even here, let us consider a tubular element in the flux path between these 2 points P1 and P2. So I consider 2 circular paths between a small distance, a small differential distance, right? So let this differential distance or differential width be some dx. Now, if I want a point from the center of this conductor onto the verge of this tubular element, so let this point be at a distance x meters from the center of the conductor. Now, in that case, if I want the MMF, according to Ampere's law, if I want MMF at point x, or MMF at some point, at a point which is at distance x, x meters from center of the conductor, that would be, according to Ampere's law, I can express it as surface integral of, if I consider the magnetic field intensity at this point, which is at x meters from center of the conductor, to be Hx, then MMF around this closed path would be surface integral of Hx ds, where ds is a small differential surface on this circular path of tubular element. So this would be MMF, and according to Ampere's law, this MMF will be equal to the current enclosed. So this tubular element which we are showing here is enclosing the entire current flowing in the conductor. So that would be equal to the I. Why? Because we have taken I to be the current flowing through the conductor. Let this be equation 1. Then if I integrate this around the closed path of tubular element, I get 2 pi x, which is circumference of the circle, multiplied by Hx, that would be equal to I. Now from this I can write Hx is equal to I by 2 pi x. Let this be equation 2. Now if I want flux density at this point. So flux density at this point, if I take it as Bx, then that I can write it as mu into Hx. So from equation 3 that becomes mu into I by 2 pi x. Let this be equation 3. Now if I want the flux in the tubular element, if I say the flux which is flowing in this tubular element is some d phi, if this flux is some d phi, then I can write flux in tubular element d phi will be equal to this flux density Bx multiplied by the area which is normal to the flux lines. Then if I consider a conductor of unit length, say 1 meter, then this becomes Bx into, now the area which is normal to the flux lines will be equal to the width of this tubular element, which is dx, multiplied by the length of the conductor. Let us consider the conductor length of 1 meter. So then that conductor length will be 1. So as a result, we may write d phi is equal to Bx into dx. But already from equation 3 we have got Bx is equal to mu I by 2 pi x. If I substitute that here, I get this as mu I by 2 pi x into dx. Let this be equation 4. Now, if I want flux linkages in the tubular element, that I can represent it as d lambda, where lambda represents flux linkages and d lambda represents the flux linkage in tubular element. So that should be equal to this d phi multiplied by the fraction of current which is linked by the flux which is flowing in tubular element. But you can see that we are considering the flux which is external to the conductor, so it links the entire current which is flowing in the conductor. So that is the reason why the fraction of current which is linked by it will be equal to 1. So in this case, the flux linkages in this tubular element d lambda will be equal to d phi. Already we have got an expression for d phi in equation 4 that I can substitute here. Then this becomes d lambda is equal to mu I by 2 pi x into dx. Now if I want flux between points P1 and P2, flux between points P1 and P2 which are external to the conductor, or rather say I would like to calculate, instead of flux, let me calculate the flux linkages between these 2 points. I can represent it as lambda 1 2. Why? Because I am calculating the flux linkage between these 2 points 1 and 2. Then that would be integral of d lambda between points P1 and P2 which are at distance D1 and D2. So the lower and upper limit of integral would be D1 and D2. So now let's integrate it. So it implies lambda 1 2 will be equal to integral of d lambda, which is mu I by 2 pi x into dx between points d1 and d2. So mu I by 2 pi is a constant with respect to x. So I can take it out of the integral. So this will be mu I by 2 pi integral of 1 by x dx. Then this would be mu I by 2 pi into log x between the limits d1 and d2. So this again becomes mu I by 2 pi into log d2 by d1. So since I am considering a unit length of conductor, here the flux linkages would be Weber turns per meter. Right. Now we know that this permeability mu is given by mu naught into mu r, where mu naught is permeability of free space, which is given by 4 pi into 10 power minus 7, and mu r is the relative permeability, that is, in this case it is the permeability of the conductor, which is a non-magnetic material. So its value can approximately be taken equal to 1. So this becomes 4 pi into 10 power minus 7. Now if I substitute the value of this mu in equation 5, I get lambda 1 2 will be equal to 4 pi into 10 power minus 7 into I divided by 2 pi into log of d2 by d1. So I've just substituted mu is equal to 4 pi into 10 power minus 7. In denominator I have 2 pi. So I've written the same 2 pi. I have substituted rest all terms here. So here I ultimately get this as 2 into 10 power minus 7 into I into log of d2 by d1 so and so Weber turns per meter. Let this be equation 6. Now if I want inductance between two points P1 and P2 which are external to the conductor, I may express it as L12, which is equal to lambda 12 by current enclosed by this flux linkage, which is I. So from equation 6, I get L12 is equal to lambda 12 by I, which is 2 into 10 power minus 7 ln d2 by d1. Since this is inductance, we have units as Henry, and since we are considering a unit length conductor, it will be Henry per meter. Let this be equation 7. So the ultimate equation now would be the one which I am showing here, that is your L1 L12 equal to 2 into 10 power minus 7 ln d2 by d1 so and so Henry per meter. So that's it for today. In the next class, we will be discussing about calculation of inductance of a single phase transmission line. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.